Some of the upcoming lessons make extensive use of interfaces, so it would be a good idea for you to have a general understanding of what they are and how they work. I touched on this earlier, so I'm sure you have some notion of what they do, but you're going to need to know a little more to really understand how programs set themselves up to listen to the mouse and keyboard. This is a simple class. It doesn't do anything, but it does extend the Canvas class, and it implements the runnable interface. I'm sure that you recall that any class implementing the runnable interface was required to contain a run method. That's how we've been doing animation. Keep the declaration of the MyCanvas class in mind while we go look at something else. This class creates an instance of the MyCanvas class and then tests it for being lots of things. This keyword, instance of, is a Java operator. This is not a method call, this is part of the language. It looks at the object to its left and determines whether it's an object of the type specified to its right. The type could either be a class or an interface. As you'll see inside a program, they act pretty much alike. We know that a MyCanvas class is also a Canvas class because it extends the Canvas class. This means it can be treated in every respect just exactly like a Canvas object, although it may act differently under certain circumstances when you call its methods, but that's not where I'm going right now. The MyCanvas object is also a component object, because the Canvas class extends the component class and the inheritance is passed on down to the grandchildren. The component class extends the object class, so the MyCanvas object is also an object. Of course, this is no real stretch because every object in Java can trace its heritage back to the object class. You may want to take a look at the documentation of the object class. Among other things, you'll find methods that are shared by every single object in Java. It's interesting. One of these methods is toString, which converts the object to a string, which means that every object in Java can be converted to a string. But you knew that. If you write a class, but you don't write a toString method, your class inherits one. But I'm getting off the main subject again. The MyCanvas class is also a runnable object. Now, this is important. If a class implements an interface, then objects of that class can be treated exactly if they were objects of the interface type. The constructor of the thread class required a runnable object be passed to it, and any class implementing the runnable interface would satisfy that requirement. Here's one that could surprise you. The MyCanvas object is also an accessible object. You see, the component class implements the accessible interface, so the MyCanvas class, by inheriting the component class, also inherits the implementation of the accessible interface. All in all, the MyCanvas class inherits the implementation of 4 interfaces, all implemented by other classes in its heritage. An object of the MyCanvas class can be treated as any one of these. Now here's how you go about taking an object of one class and treating it as the object of another. It's all done by declaring a reference of the type you wish to have and then storing the address of the object in that reference. Java is very picky about what it allows you to store in a reference. If you try to put an object into a reference to something that is not anywhere in the object's heritage, it won't let you do it. Error messages will pop out. Believe me, I've tried. There's no way to fool it. Here we have the assignment of a MyCanvas object to a reference to a Canvas object. Using this new reference gives you access only to the Canvas stuff in the MyCanvas object. Then the address of the MyCanvas object is stored in a reference to a runnable object. The compiler goes along with you on this because anything you can store in a MyCanvas reference is going to be a runnable object, so you can certainly store it in a runnable reference. Notice that although runnable is an interface, we can declare ourselves a reference to it just like we can a class. Here we create a new MyCanvas object and store its address directly into the reference to an interface implemented by a superclass of MyCanvas. You see, the MyCanvas class completely inherits the implementation of all interfaces by all superclasses just as if they had been implemented locally. If you're making an assignment in a direction such that the compiler can't be positive it will always be correct, you'll have to cast it. For example, in this assignment statement, a class other than the Canvas class could implement the menu container interface, so it is possible that this won't fit. If you force it to fit by casting it this way, and it turns out to be wrong, it'll be detected when the program is running, and an exception will be thrown and halts execution. This program will compile and run this way. Now, all of this is called polymorphism, and it's a central characteristic of object-oriented programming. It becomes extremely useful to be able to morph objects into different types of things and use them in different ways. Being able to extend classes, implement interfaces, and morph objects is the basis of all object-oriented programming in Java. You'll pick up some other object-oriented ideas as we go along, but most of them are only bookkeeping to make these fundamentals work. Let me show you an interface. As you can see, it's very much like a class. The keyword interface is used to define it, and it has methods without any code in them. There is no constructor. In fact, there is no executable code of any kind. Just like a class, you put a public interface in a source file of its own with the same name as the interface, and then you compile it into a class file just as if it were a class. Here's a class that implements the Cruncher interface. This is sort of a minimal implementation. To satisfy the requirements of the interface, bodies for all three methods are provided. And that's it. We'll be implementing some interfaces in the upcoming lessons. This lesson shows you how to teach a component to listen to input from the mouse. The example program uses a Canvas component to report the position of mouse clicks. The clicker class is a frame used to display a Canvas object of the clicker Canvas class. Notice these two import statements for things that are used in the clicker Canvas class. The mouse listener interface is implemented by a class that wishes to receive mouse input from a window. The incoming information about a mouse is stored in a mouse event object and is passed to the methods defined by the mouse listener interface. It's not nearly as confusing as it sounds. Let me show you. The clicker Canvas class implements the mouse listener interface, which means it implements the methods necessary to receive incoming mouse information. It also extends the Canvas class, making it a component. A component is capable of listening for input from the mouse and passing it on to the listeners. The addMouseListener method is a method of the component class. A component receives all input from the mouse and reports each mouse event to all mouse listeners in its internal list of mouse listeners. Besides being a component, this class is also a mouse listener, so we call this method to put itself in its own list. We could have had some other class act as the mouse listener, and we would have added it to the list instead of adding this. You can add a bunch of mouse listeners to the list of a component, and they'll all receive messages about the mouse. The mouse clicked method is one of the ones required by the mouse listener interface. It gets called every time a mouse button is pressed and then released, that is, when it is clicked. The information about the mouse click is packed into a mouse event object. This includes the X and Y positions of the mouse, along with some other useful information. For example, it tells you which mouse button was pressed and whether Shift or Alt or something else was being held down when the mouse button was clicked. There is also a millisecond level timestamp indicating when the mouse was clicked. This timestamp can be used to determine whether there was a double click or whether they are just two single clicks. But right now, the only things we're interested in are the X and Y position of the mouse pointer. Then we want to update the display to show this new location, so a call is made to repaint once we've stashed the new X and Y values. Now this method is called every time the mouse pointer enters the window. The same mouse event object is passed to show the point of entry. A mouse can enter the window from any of its sides, or even in the middle by having the window pop up under the mouse pointer. This Boolean flag is set to true to indicate that the mouse is now inside the window. Once the X and Y values of the location of the mouse have been captured, a call is made to repaint to update the display. The opposite of the mouse entered is the mouse exited method. This method is called every time the mouse leaves the window. The program doesn't care where it left the window, but the Boolean flag inside is set to indicate that the mouse pointer is now outside the window, and repaint is called so the screen will be updated. Now, two more methods are required by the mouse listener interface. The mouse pressed method is called whenever a mouse button is pressed, and the mouse released method is called when a button is released. For this program, all we need is the mouse clicked method, which sort of summarizes these two into a single method call. We'll be using these later when we start dragging stuff around the screen. The window is painted one way if the mouse is inside the window, and another if it's outside. If it's inside, the background of the window is filled with red, and the X and Y position values are displayed at the current XY location. If the mouse pointer is outside the window, it's filled with pink and nothing else is displayed. When the program is compiled and run, it looks like this. This lesson describes a program that draws a simple square in the window and allows you to use the mouse to move the square to a different location. The Mover class is a frame that's used to display a Mover canvas object. The object we're going to move around the window is a square that's 20 pixels on a side. This Boolean value is set to indicate when the square is being moved. These two values are the current location of the square. These special offset values are used so we can position the square when we put it in its new location. I'll show you how they work in just a minute. The constructor sets the size of the window and makes this object its own mouse listener. Now, the only methods in the mouse listener interface that we're interested in for this class are mouse pressed and mouse released. But the others must be present, so they're included here, but they don't do anything. When the mouse button is pressed, the first thing we need to find out is whether or not it was pressed inside the square. If the mouse X is less than the square X, or the mouse X is greater than the square X plus the side, then it was pressed outside the square and we don't do anything. The same thing is done for the Y value. If the mouse pointer is above the square or below the square, nothing's to be done and we just return. If, on the other hand, the button was pressed with the mouse pointer inside the square, we're going to start moving it. To start with, we need to record the relative position of the pointer to the XY position of the square. This is so we know how to place it at the end of the move. For example, if the mouse pointer is on the upper left-hand corner of the square that's being moved, it needs to be dropped in its new location with the pointer in the upper left-hand corner. Now, to do this, we need to know exactly where the mouse is in relation to the upper left-hand corner of the square. The offset values are stored in X offset and Y offset, and then finally we set the moving flag to true to indicate the square is being moved. If the mouse is moving, that is, if the button was pressed inside the square and has just been released, then moving is true, and the code inside this block is executed. A new location for the square is executed, taking the offsets into mind, and it's no longer being moved. A call is made to repaint to make the square appear in its new location. Now this is a very simple paint method. It paints the background of the window cyan and draws a black square at its current location. Here's how it works. There are a couple of things that are not right here. First, we don't see the square move. It just appears wherever the mouse happens to let go of the button. Also, you can move the mouse completely outside of the window, and we lose the square. The only way to get it back is to expand the window to include the space where the square was dropped. There are solutions to these problems, and we look at a couple of them in the upcoming lessons. This lesson presents a modification of the program from the previous lesson. Instead of using the mouse to move an object from one location to another and having the object simply appear at the new location, the program in this lesson displays the object as it moves. This is more the drag and drop operation that we've all become accustomed to. The mouse listener interface we used in the previous program didn't quite have everything we need now. To be able to drag an object from one place to another, we need to know where the mouse is located every time it's moved, not just the moment a button is pressed. This can be done by implementing the mouse motion listener interface. It does for mouse movement what the mouse listener interface does for button clicks. The Dragger1 class is a frame that displays an object of the Dragger1 canvas class. Now the Dragger1 canvas class implements both the mouse listener and the mouse motion listener interfaces. Remember, while a class can only extend one other class, it can implement all the interfaces it wants to. In this program, we're going to need to process mouse button presses and releases as well as mouse motion, so we need both interfaces. The declarations are about the same as they were in the previous program, but we have added a rectangle reference and an image reference. This is because we've also added an update method that uses a memory resident object to draw the images, so we won't have that flicker problem. Dragging is a form of animation, and even though the movement is not controlled by the clock, it's still movement, so we must suppress the flicker by painting the entire image on the window at once. This constructor sets the initial window size and creates a starter rectangle object. Its size being what it is will cause the update method to create a new one, but it's also appropriate for paint to use to fill the background when the window first appears. Then we call addMouseListener and addMouseMotionListener to put this object in both of its internal lists or reporting events. Remember, you must register for events or they won't be sent to you. The mouse pressed and mouse released methods are just exactly like they were in the previous example. Mouse pressed determines whether the dragging action is about to begin, and mouse released places the square at its final resting place after the dragging is complete. Here are the two new methods, the ones that are required by the mouse motion listener interface. I've never figured out exactly why there are two methods, but there are. The mouse moved method is called every time the mouse is moved inside the window if no button is being held down. The mouse dragged method is called every time the mouse is moved while a button is being held down. Now here's an important concept. If a mouse button is pressed while the mouse is inside the window, dragging the mouse outside the window still causes the method to be called as long as the button is held down. That is, positions outside the window are reported to the program until the button is released. And when the button is released, that fact is reported to the mouse released method. You'll see what effect this has in just a minute. Notice that while the square is being dragged, every motion of the mouse changes its X and Y location, and repaint is called, so the square is displayed in that new location. This has the effect of dragging the square with the mouse pointer. The update method begins by checking to make sure the current window size matches the size stored in the rectangle object. If not, a new rectangle object is created and a new image object is created to match it. Now, this program does not allow the square to be dragged outside of the window. If the X position of the square is outside the window, either right or left, its X location is adjusted to be just at the edge of the window. The same is done if the vertical position of the square is above or below the window. The paint method starts off by clearing the background of cyan and then draws the square at the current location. If the square is being dragged, it shows up in orange. If not, it shows up in black. It could have been dragged just as well in the same color, but the change should give you a better feel for how it's working. Anyway, it looks like this. Notice how it's trying to follow the mouse, but that last second adjustment in the update method won't let it leave home. In the next lesson, I'll show you another approach for keeping the dragons at home. You've had the experience of trying to drag something on the screen to a place it didn't want to go. When you dropped it in its new location, it went back to where it came from. Usually it flicks back so fast you can hardly see it move, but in this lesson I'm going to show you what it's like to move an object that keeps drifting back to its home base no matter where you put it. This program adds another interface to the program from the previous lesson and instructs the object being dragged to return to its home location no matter where else it's put. The home location is in the center of the window. As you can see, another interface has been added. This time it's our old friend Runnable. We're going to need him to have the square automatically drift back to its home position. Now this is just about as crowded as it ever gets. It's pretty rare for a class to implement 3 or more interfaces. It's often 2, but usually just 1. Anyway, this is the new reference to the thread object. The X and Y home variables have been added to contain the home position of the draggable object. Here's something you may not have seen before. 2 assignment operators on the same line. You can have as many of these as you like in a row. The value on the far right is calculated and stored in the location to its left. Then that same value is again stored in another location further to the left. This example has only 2, but no matter how many there are, they all end up with the same value. This is not an applet, so there are no start and stop methods, so the thread object is created and started here in the constructor. The run method is just like the other run methods we've seen. It goes into a loop with a timer and calls repaint at regular intervals. The calls to repaint means there will be calls to update at regular intervals. If the size of the window has been changed, a new rectangle object is retrieved for it, and the X and Y location for home is redetermined, and of course an image object is created for the new size. Now this test is made to determine whether the square is currently being dragged. If so, this program doesn't mess with the location. However, If it's not being dragged and it's not sitting on its home position, the program inches it 1 pixel closer to home. The square no longer changes color while it's being dragged. And that's everything that's new in this program. The update method was already there, so it was almost trivial to make it runnable and add the thread object for animation. If the square is dragged off center, it works its way slowly back. If it's pulled completely outside of the window, it will make its way back into the window again and head for home. Reshaping the window moves the center, moves the home, and the square heads for it no matter what its previous current location.